I'm Roger Sikowski from Webucator.com. In this video, I'm going to demonstrate a few Python exception handling tips that Asaf Gordon presented in his insightful blog article. He agreed to let us create this video to illustrate his examples. His blog article can be read at the address shown. Let's get started. The article contains recommendations for Python exception handling in programs intended for non-technical users and differentiate them from programming and debugging exceptions. Specifically, the article highlights two important points. First, do not raise or catch the generic exception. And second, use user-defined exceptions for the application level errors. Let's look at a few examples to make the point clear. The first example doesn't make any attempt to deal with an exception at all. The code will produce an exception because the reference file doesn't exist. When I run the code, I get a traceback. Let's give it a spin. The results aren't pretty. The actual problem isn't a programming issue, so all we really accomplish is to confuse the user with a useless message and a source code stack trace. We could simplify the exception output somewhat by catching all exceptions with a general exception. Here's an example of what will do that. Let's run this example just to see what will happen. The output is better. At least the user has some idea of what the problem might be, but it's really not much more than that in terms of help. Now let's try a different program. This time it produces a programming error. The statement is missing a second value for the string parameter. Let's run it and see what happens. This time the message isn't any more helpful than it was previously. It doesn't help the user, nor does it help the programmer. For programming errors, we actually want to see a traceback. As a result, this doesn't help anyone. Another example demonstrates a slightly different issue. In this case, the program contains an input error where the file contains an unexpected value. Let me run it. This is partially a programming error. The code isn't able to handle invalid input, but the error isn't helpful to the user or the programmer, just as before. In a larger program, there usually is a mixture of errors. This is especially true during development. Catching them generally makes it hard for the programmer to find out what's wrong. Consider the following code. Each function in this code is designed to raise an exception. A few of them replicate exceptions or operations that we've already seen in other examples, but there's a few others to make the mix more interesting. Briefly, we can see that in our first function, we're generating a runtime error which is about the same as we did in our very first example. In the next one, we have a value error, and once again, this is the same as the example we had seen earlier where the file had an unexpected value. A little further down, we have an attribute error, and in this case, the real problem is the read line instruction. It is a typo. There's two D's in the function. The last one is a type error, and it's just simply a syntax error. Right? There really is no Python syntax for this. The code itself runs those functions in a random manner. It randomizes the functions, and the calls are intended to simulate the conditions for a complex program. Basically, we can't tell in advance which error will happen. Let's run it a few times and see what happens. The first time I run it, what we can see is that we get an invalid literal for an int. Let's try it again. And this time we're getting not enough arguments for our string parameter. Another run at it, and we get no such directory. Well, this will continue in a random fashion. When the program runs, we get the messages for these errors, but they're all handled in a generic way because we're using a generic exception. The messages don't provide anything useful really to the user, and they're not very useful for programmers. Instead of catching all exceptions in a generic way, it's better to catch specific exceptions. At least then we can separate the messages into those indicating a programming problem and those that are non-programming problems. In this example, the functions are unchanged from previous examples. The difference is in the implementation. Here, we're using I/O error to report on, obviously, I/O errors, and value errors to report on conversion errors and other issues. In the example, they indicate user errors, non-programming errors. We want to catch them and print an informative message without a stack trace. On the other hand, attribute errors and type errors, those are bugs. When they happen, we want to pull the full stack trace for debugging. Let's run it a few times and just see the kind of errors that we might pull at different points. In this case, we're getting the user error. In this case, we get a stack trace. We can run it a few more times and we can see that we may get different ones based on the randoming of his program. But in each case, the messages are coming out in an appropriate way. One for users, one for programmers. So we've distinguished between the types of error messages that each would receive. Let's take one more step to refine this program. Catching an error in the main section might miss some information, such as value error that could originate from many different places in the code and from many different inputs. It's better to catch user runtime errors as close as possible to the source. In this version of the program, we catch application level exceptions as close as possible to that source. In this case, I/O errors are targeted to specific instances of I/O, making the message more specific about the actual problem. Modules probably shouldn't exit in this way, so they can be imported into other scripts. Nonetheless, the example demonstrates the benefit of localizing exception handling. The second function, here we have a similar fix that targets both I/O error and value error, and still provides that specific information pertinent to the actual program. The remaining functions are unchanged and still produce tracebacks that benefit the programmer. We can run our program once again. And we can see that we get our tracebacks when we have programming errors. The results of the program distinguish end-user errors from programming errors, but it does it in a more fine-grained manner. Our final refinement of this program solves the problems pointed out in our previous examples. First, terminating the program in a function that might be used in another module is bad form. Exceptions are intended to be handled and not terminated in the program. And second, the program should do more to differentiate application-level exceptions from other Python exceptions. To solve both issues, we create a specialized class which inherits from Python's exception. It can be raised when there is an application-level error, and catch it in the main code where an exit is more appropriate. As a result, our exception handling in our implementation becomes simplified without losing meaningful detail. We can give it a trial run to demonstrate some of the possibilities. A user-friendly message, and a traceback. Clearly, the code has become more adept in dealing with problems for the user or the programmer. Additionally, it manages the program's exit in a logical way. And finally, at times you may have to catch generic exceptions that can't be passed forward. Even in that eventuality, all is not lost. To determine the type of exception, we can solve the problem with a specialized catch as shown here. We can give this a spin, and as you can see, the results provide a useful message nonetheless. Thanks once again to Yosef for the inspiration for this video. Check out his blog at the URL shown here for other great articles relating to Python.